Hello and welcome back. In this section we'll be discussing hydrohalogenation, which is the first reaction in Chapter 8 in Klein Organic Chemistry. So this is an alkene addition reaction where we're adding a halo acid across that alkene. So we're adding an H to one side and then the halogen to the other side. So we're adding H and X across a double bond. Okay? So we can use either HCl, HBr, or HI. HF is generally not used. It's toxic and hard to work with. So if we have a symmetrical alkene like this one, and we're using HBr as our halo acid, then we can add H to one side, so it's not shown here. The H is over here on the left, and Br on the right. Okay, we get 76%, which is a high outcome, a high yield of this product. Okay, so for a symmetrical alkene, that's fine. Notice that the temperature is kept low at -30, so it's kept really cold just because it's an addition reaction. Like we talked about, if you heat it up, you're going to get the reverse reaction. But what if you have an not a symmetrical alkene? It's not symmetrical on both sides of the double bond. Then we have two regioisomers possible, and that's going to depend on which regioisomer we get is going to depend on which side gets the H and which side gets the X. So in other words, the question marks here are showing where does the H go and where does the X go. So we're going to be looking at that. It turns out that hydrohalogenation is regioselective, and this regioselectivity is called Markovnikov Addition. So in 1869, this guy named Markovnikov observed that the hydrogens on that are adding to these alkenes tend to add to the carbon already bearing more hydrogen atoms, and the bromine or the halogen adds to the carbon that's already bearing more alkyl groups. So in other words, you might say the rich get richer. The ones with the side with more alkyl groups or more carbons is going to get the halogen. The side with more hydrogens is going to get the hydrogen. Okay, so here we have this vinylic position currently bearing one hydrogen. Okay, so on the double bond on this side we have one hydrogen, and on the right side we have no hydrogens. That means that the hydrogen is going to go to the left side and the bromine is going to go to the right side. So we're adding, so what are we adding and where are we adding it? We're adding H and Br across a double bond. Okay, and we're adding H, in this case, to the left side because it has more hydrogens already, and we're adding Br to the right side because it has more alkyl groups. Now, it would be a good idea for you to make a flashcard with, with all of these reactions, and you should go back and do that if you haven't yet, for your SN1, SN2, E1, and E2 reactions. And so on the front, you're going to put like this alkene here. Okay, so this is going to be your front, and you're going to say, oh, I didn't draw that very well. And put an arrow, and then on the arrow put HBr. And on the back, you're just going to put your product. Okay? So just get you some some blank index cards and make some flashcards. And yours will probably look better than mine. And do this with all of your reactions so you can practice. All right, and so we learned that the halogen is installed at the more substituted position. And we're going to look at why that is in just a few minutes. We're going to look at that in more detail. But something that other chemists found out, they thought that Markovnikov, this guy, was just wrong. They found that just the opposite happened, that their hydrogen went to the more substituted side and the bromine went to the less substituted side. Well, it turns out that Markovnikov was really good at cleaning his glassware, and he didn't have any peroxides in his glassware. Generally, when you're doing organic chemistry reactions, peroxides are going to build up in your glassware, and if you have even traces of peroxides, those act as a catalyst and cause the opposite regioselectivity. The hydrogen goes to the more substituted side, and the bromine goes to the less substituted side if you have a peroxide catalyst present, and that's called anti-Markovnikov addition. Now this reaction mechanism goes through a radical mechanism, and we will look at that mechanism when we get to the chapter on radicals. So it has a different mechanism, but for right now, know that you get the opposite regiochemistry if you have peroxides in your flask. Okay? So the important lesson here again is that regioselectivity of HBr addition, and this is just for HBr actually, with the peroxide. The HCl and the HI will add Markovnikov, but they don't add in the anti-Markovnikov reaction, and we will look at why that is in the chapter on radicals. But for HBr, you get anti-Markovnikov addition if you have a peroxide in the reaction flask. And you get Markovnikov addition if you don't. So keep your glassware clean. You're going to get Markovnikov addition if you have traces of peroxide, or if you want the anti-Markovnikov addition product, you can use a peroxide catalyst. Alright, so let's look at the expected major product for the following reactions. So what are we adding and where are we adding it? We're adding on this first one H and Br. Where? Across a double bond. Okay, so the H is going to go where? Let's notice that this side has a hydrogen already. The other side does not. Okay, so that's the side that's gonna get the bromine. Okay, I don't want you to think that I'm drawing a mechanism here, so I don't want to put a bromine out there like it's going there, but let's draw. I'm sorry, I don't know why I did that. I need to erase that double on there. Okay, so so our bromine is going to go to this side, and our hydrogen is going to go to the less substituted side. So bromine goes to the more substituted side, hydrogen goes to the less substituted side. Okay, so that would be our product. And so for the next one, we're also adding H and Br across the double bond. Okay, and let's just draw our structure here. So the Br is going to go to the more substituted side. The H is going to go to the less substituted side. So there was a hydrogen here. Now there are two hydrogens on that carbon that had one. Okay, so I didn't draw the other hydrogen up here. We could just go ahead and draw it in if it makes things clearer. All right. So we can do a few practice problems if you'd like before we move on. We just actually did A, so let's go ahead and do B. Notice that B has a peroxide present, and this is problem set 8.1 in version 3 of your book. It's a different problem set in version 2. You can figure out what that is. So now our double bond is where I just drew this last line. Okay, notice that there are two hydrogens over here, and so that's the side that's going to get the hydrogen, because what are we adding and where are we adding it? We're adding H and Br. Oh, I'm sorry, we have peroxide here in the pot. No, so that's the side that's going to get the bromine. Okay, so we get anti-Markovnikov addition here. So now we have a bromine on the right side. Okay, and we had two hydrogens there. Those are still there. And we had no hydrogens on the left, but now that hydrogen is going to go to the less substituted side. Okay. All right, so for C, we already did C in the previous example, so that was B. Now don't forget, there are hydrogens over here on these other carbons. We just didn't draw them in. We just didn't draw them in for clarity. All right, now so for D, product for D, over here we've got a hydrogen. We don't have any peroxide, and this is HCl anyway. So the chlorine goes to the more substituted side. The hydrogen goes to the less substituted side. I'm going to leave this hydrogen that I drew over here out. I'm not going to put that one on there. I'm just drawing in what we're adding. So we're adding H and Cl, okay? So we added H to the less substituted side, Cl to the more substituted side, okay? The next one is Hi. Okay, so what are we adding and where are we adding it? We're adding H and I across the double bond. The H is going to go to the less substituted side, and the I goes to the more substituted side. Okay, and the next one, we've got peroxide present. So we're going to have anti-Markovnikov addition. That means the hydrogen goes to the less substituted side. Which side is that? Notice this one has a hydrogen here. The hydrogen goes to the more substituted side. So this hydrogen that was here, that side's actually going to get the bromine when we use when we do anti-Markovnikov addition, and the side that had no hydrogens is going to get the hydrogen that's added. So we're adding H and Br. When we do anti-Markovnikov addition, the less substituted side, or the side that had a hydrogen on it, is going to get the bromine. So we'll go ahead and draw that other hydrogen in that was already there. And the side that had no hydrogen is going to get the hydrogen. Okay? So let's identify the reagents we would use to achieve the following transformations. Aren't these exactly the same? I'm confused. All right, so we have anti-Markovnikov addition, okay, and so we're going to use HBr in the presence of peroxide. I think they wanted us to have a different product here. How would you get that? You would just use regular HBr, because this is Markovnikov addition. And this is anti-Markovnikov at the top. Okay. All right, so let's look at the mechanism of why this reaction occurs the way it does, and how do we get Markovnikov addition. So this mechanism is a two-step process. In the first step, the alkene is acting as a base, picking up a hydrogen from the halo acid, okay? And when that first reaction arrow is used to pick up that hydrogen, then the bond between the hydrogen and the bromine is broken, and the bromine takes the 2 electrons in that bond with it in the form of a lone pair, okay? So now we've got, what did we form? We formed this carbocation where the hydrogen went to the less substituted side. Why did that happen? Because the carbocation is more stable on the more substituted side, remember? So the carbocation is going to go to the more stable spot. That's why the hydrogen goes to the less substituted side. Now this bromine that was kicked out is hanging around, and it can actually add to the carbocation because this is a nucleophilic species. So the first step is a proton transfer. The second step is nucleophilic attack. So it adds there to give us our product. So notice on this product we have Markovnikov addition. The bromine goes to the more substituted side. The hydrogen goes to the less substituted side because the carbocation is more stable on that more substituted side, and so that's why the nucleophile attacks it there. So if we consider the energy diagram, it is a two-step process where first we get the proton transfer and then we get nucleophilic attack. So the rate determining step is this activation energy here, the first activation energy, because that's going to be the formation of that carbocation from the addition of that hydrogen. And then the second step is going to be shorter, and so that's going to lead to the product. Notice also on this energy diagram we have an intermediate here in that valley. Okay. So the anti-Markovnikov pathway, if that were actually the mechanism observed or the product observed from this mechanism, would have resulted from a secondary carbocation intermediate from this starting material, whereas the Markovnikov pathway results from a tertiary carbocation intermediate from this particular starting material. So obviously the tertiary carbocation is more stable than secondary, and so that's going to be more likely to give us the product. So a secondary carbocation, as you can see here, in that first step, the addition of the hydrogen and the formation of that carbocation, the secondary is higher energy than tertiary. So tertiary is going to be our major product. So let's draw a mechanism for these transformations, okay? So for A, I didn't put these each on their own page, so we'll have to redraw them if we go through all of them. I may not do all of them. Okay, so what are we doing? We're adding, what happened here? We added HBr across this double bond. We added we added Br to the left and H to the right, right? And so why does that happen? Okay, so in the first step, the double bond is acting as a base, picking up the hydrogen, and that breaks the bond between that hydrogen and bromine. And so we end up with a carbocation formed. Okay, and now we've got, I'm going to draw it in a different color. Now we've got a hydrogen over here where at the less substituted side. Okay, and a carbocation, a tertiary carbocation here. Now in this next step, we've got the bromine hanging around, okay, with its lone pairs. And so one of those lone pairs is going to attack the carbocation. So that species is acting as a nucleophile. Okay, and that's going to give us our product, which is the Markovnikov product, where the bromine is at the more substituted position and the hydrogen is at the less substituted position. Okay, for the next one, we've got what did we have? We have this, and we've got a double bond right here. Okay, so in the first step, we've got the double bond acting as a base, picking up the hydrogen. The chlorine gets kicked away and takes its 2 electrons from the bond with it as a lone pair. Okay, and so in the next step, we've got a carbocation formed at the more substituted side. That means the hydrogen went to the less substituted side. Okay, so now we've got the chloride hanging around because it got kicked out with its bond becoming a lone pair. And now one of those lone pairs can attack the positive charge of the carbocation and give us the product. Okay, and that's this. Now I didn't draw the hydrogen in that was added, but we can go ahead and draw that hydrogen that we added, because we added H and Cl across that double bond in Markovnikov fashion. I think I'll let you guys work that last one on your own, see if you can draw the mechanism. Now, we had regiochemistry for this reaction, but we also have stereochemistry to worry about. If the addition of that halide forms a chirality center, then it will be we will have stereochemistry to worry about. So in general, we form equal enantiomers of R and S for the products. Okay, so we're going to get a racemic mixture of products. And why is this? Because remember, in the first step in that mechanism, we're going to form a carbocation, and the nucleophile is hanging around and can attack from either side. Okay, it can attack from either side. And if it attacks from, in this case, the top side, we get the first stereoisomer. If it attacks from the bottom side, we get the second stereoisomer. So we get a racemic mixture of products. Alright, so let's predict the products for each of the following reactions and try to decide whether we've created a new chiral center. Okay, so for A, what are we adding and where are we adding it? So first we need to consider regiochemistry, and second we need to consider stereochemistry. Okay, so we're adding H and Br across that double bond. So let's erase that double bond there. Let's see if I can erase it. Okay. Okay, and we're adding Br to the more substituted side. So that was this side, and the H went over here, okay, to the less substituted side. Now, we have to ask ourselves, did we form a chiral center? Well, we didn't form a chiral center at the hydrogen because there was already a hydrogen there. So that's not a chiral center. Let's consider if we formed a chiral center at the bromine, at the carbon bearing the bromine, okay? Well, that carbon has bromine, methyl, ethyl, let me get a different color here, ethyl, and propyl. So it has 4 different groups attached, therefore that is a chiral center. So how would we properly draw this chiral center? We can draw the bromine going back and the methyl coming out. So we're going to get that enantiomer, and we're also going to get the opposite enantiomer where we have the bromine coming out and the methyl going back. So we're going to get a racemic mixture. So you can just draw one of these enantiomers and then write plus En to indicate that the other enantiomer is formed. That's perfectly acceptable for most teachers. Okay. So for B, what do we have here? So we're putting what are we adding and where are we adding it? We're adding H and Cl across the double bond. H and Cl across the double bond. The chlorine is going to go to the more substituted side. And remember, the rich get richer. Okay. The hydrogen is going to go to the side that has a hydrogen already. Okay, so the chlorine's going to go here, hydrogen's going to go here. So let's put that chlorine here. We can leave the hydrogen off because we don't really need to put it on the product. Now, is that a chiral center? Okay, so that carbon now has chlorine, methyl, 1, 2, 3 propyl, and 1, 2, 3 propyl. So that is not a chiral center, so we do not need to indicate stereochemistry. Now, I generally don't dock my students if they go ahead and put a wedge and dash here, but some teachers will do that, so be very careful, okay? Now, what are we adding and where are we adding it? We're adding H and Br across the double bond, and I went ahead and redrew this because we're getting a little messy here. Alright, so the Br, now remember these arrows are not mechanism arrows, so I'm just showing you where they're going. The Br is going to this side, the H is going to this side, okay? So in our product, we're going to have Br here. Now, is this a chiral center? Okay, so this carbon has, let's go ahead and circle ethyl, bromine, okay, this path around the ring, and that's different from this path around the ring. So those two paths around the ring are different, therefore there are 4 groups attached to that chiral center, and therefore this is a chiral center. So We have ethyl, we can put that on a dash. We can put the bromine on a wedge, it doesn't matter. You can put the bromine on a dash and the ethyl on a wedge. And then just put plus En. Okay. If you want to draw the other enantiomer, you just put the bromine on the dash, the ethyl on the wedge. Alright, now for D, I'll go ahead and redraw that one. So what are we adding and where are we adding it? We're adding H and I across this double bond. I'll go ahead and get a different color. The iodine is going to go to the more substituted side. The H is going to go to the less substituted side. Notice there was already a hydrogen there. Okay, so for our product, let's just go ahead and draw it without a chiral center. Okay, now let's figure out if that carbon bearing the iodine is a chiral center. So it has iodine, methyl, this path around the molecule, and that's 2 carbons away from those 2 methyls, and this path around the molecule, which is actually also 2 carbons away from those 2 methyls. So that is not a chiral center. That molecule has a plane of symmetry, and therefore it is not chiral. So we don't need to draw the wedge and dash. Right now, since we form a carbocation, we actually can get rearrangements, so we always have to be careful with that. In this case, when we form the carbocation here, because the double bond is acting as a base, picking up the hydrogen, we form a carbocation here. This one's secondary. Through rearrangement, through a hydride shift, this carbocation can become tertiary. So that's more stable. It's more stable, and therefore it will happen, and our nucleophile will add at that carbon instead of the carbon that originally formed the carbocation. Therefore, our product may be an unexpected product. And so it turns out that rearrangements can and do occur. In fact, this rearrangement product here gives us our major product, and the secondary carbocation leads to a minor product, which is still pretty significant at 40%. I mean, if you wanted to make the thing on the left and you wanted to do it cheaply and you had a lot of that starting material lying around, you could certainly do it if it was easy enough to separate these two by something like distillation. So let's draw a mechanism for the following transformations. Going from left to right, you see that we have added a bromine. So what have we done here? We've added a bromine, but we added the bromine over here, okay? The bromine was not added at the more substituted position on the double bond, okay? So let's look at that mechanism and see why that might have happened. All right, so in the first step here, we're adding HBr. And again, it doesn't really matter if you put that HBr over the arrow or if you just say plus HBr. Generally, as a reagent, it's going to be put over the arrow, but you can also do it this way. So the double bond is going to act as a base, picking up that hydrogen, bromine. The bond to the bromine is broken, giving us this species as an intermediate, and it's a carbocation. So it's a little bit unstable, and it can actually rearrange. And we look around and we see what we have, and we actually have a hydrogen over here. If that hydrogen shifts through a 1,2 hydride shift, then the hydrogen has moved here, okay? And the carbocation has now moved here. Okay? So now the bromine that's hanging around will attack where the carbocation is now. I didn't mean to circle that. I meant to put plus Br there. I don't know why I did that. Okay, so the bromine is going to attack this carbocation and give us our product. Oops, I meant to change colors and it didn't work out. So we see that we can get rearrangements. So for the next one here, we had a similar situation, if we form a carbocation here, okay, because the hydrogen is going to go over here, then we also have a hydrogen here that can shift. So I'll let you guys work through that one. Alright, so let's take a look at this one. I'll go ahead and draw this mechanism because it's a little more tricky. So we have HCl, and this double bond is going to pick up a hydrogen. Okay, and now we've formed a carbocation, let's say here. Alright, and so what do you think is going to happen? We can actually get a methyl shift. The methyl moves over. I'm going to leave that hydrogen off because we don't need it anymore. Methyl moves over here, and now we've formed a tertiary carbocation that can react with that chloride that was kicked out. And so the chloride attacks, and we get the product. Okay, and that's all for hydrohalogenation. We'll move on with Chapter 8 in the next video.